Anyway, so now, please make sure that this is 6.2. We finished it already. There are two checkpoints, right, from 6.2, which are checkpoint 4 and 7. You could refer to them when you try those problems. Okay. They are, but textbook doesn't have answers. So those are the part questions that you don't have, answers for, and that's what we did them in class. Yeah, that's the same exact, and that's why I named them checkpoints. The same thing from we're looking for. All right, so now today we're gonna do 6.3. And listen to the title of 6.3. Double angle identities. As I said, yeah, I'm gonna have to introduce more identities. All right. So double angle identities. All right. So, well, what is double angle? It's like 90 is the angle, which is 45 gets double, right? So that's one of my double identity, double angle. But I mean, the way you think about, say, multiplying 45 degree by 2 is like just adding 45, right, to another 45 degree, right? It's just adding to, identical numbers. But we had the tools, right, for adding up angles. That means if I want to get an identity that looks like cosine of 2 alpha, right, doubling the angle alpha, or sine of 2 alpha, or even tangent to alpha, can I manipulate the cosine of alpha plus beta in such a way so it can turn it into some identity about cosine 2 alpha? How could we do that? Divided by 2. Divide what by 2? But I want twice as much angle. Well, we will have half angle in the future, but right now it's doubling the angle. Please don't forget that those angles, alpha, beta, are arbitrary. They are any kind of angles you want. Right? So whatever you want them to be. So if I want 2 times alpha, isn't that just alpha plus alpha? But I know how to add up alpha and a beta, right? Can I just make the beta become alpha, like replace the beta with alpha? So, because if beta could be anything, let me just replace the beta with alpha. And now we realize that if alpha plus another alpha, you get cosine 2 alpha, right? So if you make the replacement on the right-hand side, so you have cosine alpha, right? Then cosine beta, which is still cosine alpha, right? Alpha, beta becomes alpha, minus sine alpha times sine alpha again. And you simplify it, it's cosine squared alpha minus sine squared alpha. And that's the double angle identity for cosine. Okay. Yes, it is another one, right? So adding to the list, but it's not that much different from the one you already know. Or it's more like a special case, right, for the sum of the angle for cosine. Okay, so now let's do the same thing to get the sine of double angle. By looking at the sum of the angle for sine, right, and replacing the beta with alpha. Okay, so now on the right hand side you have sine alpha times cosine alpha, right, plus cosine alpha times sine alpha, right? But are those two terms identical to each other? Well, the order is, different, but it's multiplication, right? So it doesn't really make any difference. So therefore, you can simplify the right-hand side of this identity by writing it as 2 times sine alpha times cosine alpha. Indeed, that it looks very different from cosine of double angle. But that is, the hard part of it. As you're getting more identities, even though they are related to the ones you know already, but they could also be superficially very different. Okay. So one more, that is the tangent of a double angle. Again, you're just making the beta become alpha, right? So you have tangent alpha plus tangent alpha over 1 minus tangent alpha times tangent alpha, and simplify it. So on the top, you get twice as much, right, of tangent alpha divided by 1 minus tangent square alpha, right? That's the tangent double angle. Okay. All right. Yeah, 3 more added to the list of all the identities you need to know for the chapter 6. Okay. All right. Refer to the review worksheet or the quiz packet. Quiz packet is going to be for 6.1 to 6.3, right? That's pretty much, if you can prepare yourself seriously for the quiz, then I'll say that it's more than 70-80% of the test, right? Or you should be able to perform just fine, when it comes to those 3 topics. But then you have the 6.5, right? But since I didn't have you guys to work on any problem for the 6.5 in a quiz, then I'll have to do more work in a class to go through those test review questions. Okay. Yeah, Max.
So you said the assignment was like a quiz. Should be on the quizzes tab or like practicing or
Wait, what are you talking about?
I don't know. What were
Oh, you're trying to find out that quiz assignment?
yeah.
So it's under assessment, then assignment, and you see the quiz 6.1 to 6.3.
Okay. Because I couldn't find it. Thank you.
Okay. All right. Now let's use those identities to work out a certain problem, which, as you will see, that you get this kind of problem on the quiz as well. All right. So the same kind with just different angles. Would you use? Sometimes they tell you sine theta is equal to this, right? Or they tell you tangent theta is equal to that. But it's the same kind of problem. So instead of telling you the angle theta, they say sine of this angle is 4/5, and the angle is in the second quadrant. And let's find out the exact value of sine of 2 theta, cosine 2 theta, and tangent 2 theta. But I hope that if you see those questions in the test, you should realize that they're just, I don't know, like almost screaming at you to use the double angle, right? As long as you know what double angle formulas are. So I'll guess, sine 2 theta, right? If you still have that formula on your notebook, you can take a look, but you don't have to memorize it at this point. I just told you, it's a new identity. But it goes like 2 times sine of the angle before you're doubling it times cosine of the angle, right? I know that we're using the alpha, right? But just a change of a label. We have sine theta, which is 4/5, but I'm missing the cosine theta. The question becomes, how will I find out cosine theta if I know what sine theta is? Provided the angle is in the second quadrant. What did we do last time? You guys remember? The triangle, yes. Yeah, so we do the triangle, label the angle theta, right? And the sine theta is 4/5, so it'll be 4 to be opposite, 5 is the hypotenuse, the missing side, adjacent side will be 3. So then you realize, oh, cosine is nothing but 3/5. Or is it just 3/5? But what about the angle being the second quadrant?
It's negative.
It will be negative, yes. So that'll be those little traps in the test. All right, so pay attention to the angle. All right, so now since we know the cosine theta, right, and the sine theta is given, so I can work out sine 2 theta, right, just by plugging everything. 2 times sine theta, which is 4/5. Cosine theta is negative 3/5. Right, just multiply them all. Right, numerators by numerators, you get negative 24. And multiply the denominators, you get 25. Right, and that's all. So again, it's literally the first step that you have to memorize or recall to use the proper identity, right? But once you figure that out, I mean, those skills are more fundamental, like drawing a triangle, figuring out the missing trig functions, right? Not to mention you've been practicing for so many times. It shouldn't be too hard as soon as you figured out what to do to be the first step. Okay. Now letter B, what I can do is I'll write down the formula for you guys since you just learned it, and you figured out the substitution and some basic algebra. All right, cosine 2 theta is cosine squared theta minus sine squared theta. And you guys go ahead and substitute the things we know about sine theta, cosine theta, and tell me how much that is equal to. This is already?
Oh, I did it before you.
Oh, okay, cool. What do you get?
-1.
Oh, okay. Is it because you thought that it's a plus for some reason?
Yeah, I was confused.
So I think I should emphasize that cosine square minus sine square is not in a pattern of the Pythagorean identity. It's cosine square plus sine square, right? That could be converted into 1, but it's a subtraction. And that's why it deserves to be a different identity. Or if you're thinking about, I mean, I could factor out the negative sign, but you might want to be careful why, to do that. Anyway, so I'll say that just to be safe, plug in the things you know about cosine. So it's well, you know what? Let me put it down. Okay, so I'm gonna square the negative 3/5, right? And I'll subtract the square of 4/5. All right, so what I should get is 9/5, not 9/5, 9/25, 9/25 minus 16/25, right? So I should be getting negative 7/25. Okay. So be careful because I think that in a test it might very likely happen that you realize, oh, it's sine square, cosine square, that you're so used to referring to the Pythagorean identity, so you thought it has something to do with a 1. No, it's very different from that identity, just because that negative sign. Okay. Now that we have sine of 2 theta, cosine of 2 theta, in letter C, well, even though you can tell that they designed it to be just a direct application of double angle for tangent, right? But do you see that we could have just used the quotient identity to get tangent as well, right? And that's why, I said, I mean, literally, whenever you're thinking about tangent, it won't hurt if you're thinking about it's just the ratio of a sine and cosine, okay? So now if you, yes.
So if it's like that,
Mm-hmm.
can we use that regular tangent thing?
Oh yeah. So the pattern, not the actual number you put into the tangent, should be the one that you just saying. So let's say tangent equals sine over cosine. So that's what we call quotient identity, right? So as long as you're putting the same thing for each of those guys, whatever you put in, it's gonna work, guaranteed. You have theta here, it's the same thing as sine theta over theta, sine cosine theta. If it's 2 theta, as long as the angles are matched, and that's why we call it identity.
So I think it's like the tangent alpha plus beta and put as like sine alpha, it's gonna work still.
Oh yeah. So that's essentially what we did to prove the sum identity, right, for the tangent. So that's indeed correct. Right. To see that, you shouldn't be too crazy about what's inside the function, right? So look for the pattern. Okay. All right. Now what is the sine of 2 theta? Well, it's negative 24 over 25. You're gonna have to divide it by negative 7 over 25, right? So the division of two negative numbers become a positive quotient, right? At least that we figure out the sign correctly, right? It's positive. Then you do the key change flip, right? 24 over 25. Multiply 25 over 7. 25 cancel. So you're left with 24 over 7. And it's positive since the two negative numbers divide each other, right? Now, I mean, you could seriously try the double angle identity, but I think that's probably not as easy as the quotient identity, but nothing wrong with it. Okay, so you can seriously try 2 tangent theta over 1 minus tangent squared theta. But the problem is you don't have the tangent theta, right? So now you don't have to do it, but is it possible you can tell me how much tangent theta based on the same sketch?
Yes.
Yes, what is it?
You just the opposite over the adjacent, which for this one is 4/3.
I'm gonna ask, is it possible negative?
Oh, it's negative.
And please make sure that you do the same thing to yourself, right? In our test, because you know that you're so close, and you know what? This is probably the only reason I'm gonna take up a point. And you could be wrong with let me put it this way. If some reason that you're looking at a sketch, you tell me that the tangent theta is negative 3/4, not negative 4/3. I feel bad. I might feel like giving you a point. Because that's I think sometimes hard to think about opposite adjacent and adjacent opposite, right? But if you don't have that negative sign, yeah, 4/3. To me, that's more wrong. Because you realize the angle is not a acute angle. Make sense? Because I'm thinking that hey, under pressure, that I might even do the same thing at 4/3, right? Instead of 3/4. But how about I miss that quadrant, right? So make sure that ask yourself, notice some of the little traps, right? All right. Now, I have some bad news for you. That turns out that we have 2 more different versions for cosine to theta.
Can we just use the one you showed us before?
You could. I'll try to answer that. I'll try. Yeah, seriously, I will try. Yeah. I'm paid for do that. I'm paid for.
You could just tell her that you showed us, and that was like, we will snitch on you. I promise. Like, I promise. Like,
Wait. So.
you don't have to find an answer. I'm just like really trying to understand the reason. Like, why are there two different versions? Like,
Mathematically?
no,
Seriously?
because that's gonna be a rabbit hole that you're not gonna.
That's one way to put it. I think I have a way to at least try to make some sense of why there are different versions.
We got this.
I feel obligated. Just try to think that these are just more options that at least that sometimes you don't get stuck with just one option. Right.
Test, there are gonna be these two different versions that we have to solve.
I know, yeah. That's okay, good. I'm glad you put it that way because sometimes we have no choice. To face what yeah. What would you be happy with you get to apply multiple colleges and multiple colleges is going to review your application. It's just not one. Let's say, can you imagine that if you're going to get to apply for one college, whether or not you like it or not, you're going to have to go in, and the only answers you get is you're getting it or not. Or you can wait for 10, 20 colleges, right? And some of them will turn you down, right? But at least that you have more options, right? Or in the future that if you think that you're doing neuroscience, neurology, right? Maybe you like medicine a bit more for some reason, or you like something else, right? Maybe you want to do psychology, right? But you want to have your option open, right? So then again, I think that it's always better to have more options, right? And you never know when you're gonna need them. And then also in the future that when you have more money and don't put them all in a bank, right? So investment, that's why they say don't put the eggs in the same basket, right? So you want to have more options. Anyway, but hey, I already told you that it's a bad news, so I did warn you. So yeah. But the two other versions are understandable, because this is basically by combining the primitive form, and I'll call it equation number 1, with the famous identity, right? The Pythagorean identity. So let's say if this is what I call equation number 4. So you know what? I'll call this one number 2, number 3, right? So let me isolate let's say sine square from equation number 4, and what you get is sine square. Okay, you guys tell me if I isolate sine square, what do I get from the 4th equation? Some say 1 minus cosine square, right? Yeah, just by subtracting cosine square. So if I call that equation number 5, now I want to substitute 5 into 1 to you know what, to the right hand side of 1 to eliminate sine square. Now, do you see that? I can write the left hand side the same as before, right? The right hand side, whenever I see sine square, I'll do some replacement, right? I'll copy the cosine square, and it's minus sine square. I'll replace it with 1 minus cosine square theta, right? So I hope that you can just get rid of the parentheses, but notice there's a preceding negative sign. It'll be cosine square theta minus 1, but plus cosine square theta, right? And therefore, we have proved cosine 2 theta can also take the form of 2 times cosine square theta minus 1. Okay, so that's literally what second identity looks like. Right. All right, so now you see that if I were to isolate the cosine square from this equation, right, and I'll substitute it back into the first equation to eliminate cosine square, we'll be able to write the first equation in terms of only a sine square on the right hand side. Okay. And also you do want to see that those equations might be used in certain cases where you do not want x or sine and cosine get mixed up, right? So maybe you want to have the version of the cosine 2 theta just about cosine or just about sine, right? And those are the occasions that you might want to think about the two alternative versions, okay? But you know, all three should be on the cheat sheet, but this is the primitive form, right? And the two other forms are basically combining the primitive form with the Pythagorean identity. All right. Now let's take a look at one more example or checkpoint question. You could probably identify certain occasions when you're better off with those two additional versions with the cosine 2 theta. Okay. Now that's what they call a triple angle identity. But this time you're not gonna have it on the cheat sheet, right? You don't have to remember it. And as far as I understand the level, the scope of the course, I don't think that you ever have to really, prove something that complicated. Okay. But we're doing it as a demonstration, just for you to see, you get to use the new tools, right? But yeah, but if you seriously Google, the trig identities, I'm sure that you're gonna see a long page on Wikipedia. But we know the sum of the angles, right? Different sum of the angles. We have the doubled angles. That's good enough. Once you go beyond doubled angles, it gets tedious. So I don't think that it's seriously not going to be that useful anymore. Now, but if you remember, to verify identities, when you're picking either left hand side or right hand side to get started, I keep saying in 6.1 that you should pick the more complicated side, right? So in this case, you have to say that the right hand side might be more complicated, right? But I insist that you might want to start from the left hand side in this case. So the reason being, as you go from the right hand side to the left hand side, it's done by condensing them, right? So this is like assemble all the little pieces into a whole Lego set. But if you go from left hand side to the right hand side, it's like you break the whole set into pieces. And that happens to me a lot of the time. When I bought like a fancy Lego set, for example, the Batmobile, right? For my son, it's like 300 pieces, right? And I wish that he can build a set and put it on the shelf as a decoration. But he's gonna break it. He can easily build it, and a few days later, it's just all the black pieces all over the place. So that's why I stopped buying those, easy, Lego pieces. Anyway, but the thing is, that bothers me is it took, say for took him, a couple of hours to build the whole thing because it's hard, right? But it's easy to break it down. So that's why here you think that if you have something that seems pretty simple, sine 2 theta, if I wanted to extend it because we have the tools to do it, it might be easier to go from the more complicated side to condense to make it all become one single term, right? Yeah, but how do I break down sine 3 theta? You can think of that as 2 theta plus theta. And you probably see why, since we have the tool to break up the sum of two angles, right? We also have the tool to deal with 2 theta, right? Double angle. So sine of sum of the two angles takes the form of sine of the first angle, right, times cosine of the second angle plus cosine 2 theta times sine theta. Okay. Keep reminding yourself that you want to get all the sines, right? You want to expand them, right? Get to the sine and sine cube. That means I don't want to see sine 2 theta or cosine theta or cosine 2 theta, right? The only thing I like is sine theta. So let's record sine 2 theta is 2 times sine theta cosine theta, right? So I'm going to replace sine 2 theta with those guys. Now cosine 2 theta, we have 3 forms, right? Which one you think that would be better for this case? So now, if you do put down the primitive form, it might still work out. But the problem is, later on, you're gonna have to multiply this guy with the sine, right? Well, it will hit the sine square to get you sine cube. That's actually what you want to see on the right-hand side. But when it hits the cosine square, it's making the power a bit too high. We want a higher power, but not in cosine, right? We want the higher power in the sine. So maybe you can use another form that only has the sine square in it, right? And we have to have that for cosine 2 theta. All right, so let me refer you to the alternative form of cosine 2 theta, which goes at 1 minus 2 times sine theta squared, right? Now there you go, right? So let's go ahead and conclude that we can now write the left-hand side as so this is 2 times sine theta times cosine theta times cosine theta. Okay. Now this guy is 1 minus 2 sine squared theta times sine theta. Okay. So again, please keep track of all those terms and see where they go. So all I did was replacing sine 2 theta with the right-hand side of double angle identity, right? I was replacing the cosine 2 theta with the right-hand side of one of the alternative form, right, for cosine of double angle. Of course, you have the cosine multiply itself, right? So you get 2 times sine theta times cosine square theta. For the second part, you would distribute the sign. You get negative. When sine hits the 1, you get sine theta. Right? When it hits the second term, it's 2 times. Oh, sorry. There's a plus sign, right? It was a plus. So I don't need the parentheses anymore. All right, so basically distribute the sign, you get the first term over here, sine theta. The second term here will be 2 times sine to the third. Now what do we do? Please compare what we have arrived from the left-hand side and what ultimately you want to go into on the right-hand side. We have some sine cube. Have the sine to the first power, but we still have the cosine square. How do we get rid of it? Was their identity, which is pretty handy when it comes to relating sine square to cosine square. Pythagorean identity, right? So yeah, that's actually the things we keep using. So now, again, if you recall, sine square theta plus cosine square theta is 1. So now if I isolate the cosine square theta, it will be 1 minus sine square theta, right? Therefore, now we can further rewrite the left-hand side as, remember that I was pausing at this moment, right? And now I do have the 2 sine theta. Whenever I see cosine square, I'll replace with 1 minus sine square theta, right? Plus sine theta minus 2 times sine to the third theta. Another random distribution, right? So distribute the 2 sine theta into the first pair of parentheses. 2 sine theta, right? When it hits the 1, when it hits the sine square, you get negative 2 sine to the third plus the sine theta minus the 2 times sine to the third. All right, so combine the like terms, right? So you get 3 times sine theta. And also you have the cubic term, right, gets combined as negative 4 sine to the third theta, right? And that's indeed the same as the right-hand side. Okay.